So the midterm is, well, the average is pretty high, I guess. It's much higher than many of my the other classes that I teach. But so it's great. It's great. The second midterm will be kind of pretty much the same thing, where most of the exam will consist of, basically asking you to give some definitions and give some suitable examples and so on, but maybe with a couple concerning very minor calculations. So in this particular midterm, the first 8 are basically definitions and explanations of concepts and so on and so forth. The last 2 involve some small kind of quantitative sort of manipulations. So I'm going to give the solutions to you, but only for the last 2 problems, because the first 8, I guess, basically you can find within your lecture notes. After you get the solutions, if you want to talk about your exam, please come back and talk to me about it. And as I said, the second midterm will be pretty much the same thing. Okay? There you go. All right, so in the meantime, let us continue to talk about the Lorentz group. It's a very fascinating story. We will barely be able to scratch the surface, so to speak. But I do want to show you the fascinating relationships that exist between several different things in telling the story of the Lorentz group. Yeah. Oh, sorry. So as I said, for those of you that just came in, for the first midterm, the average is this, okay? Please come and talk to me if you have any concerns about the test, if you have any questions, and so on and so forth. As I said, I'm going to send out the solutions to you, but only for the last 2 problems, because the rest of them are just basically matters of definitions and some simple examples, which you can find in your lecture notes. Okay, so onwards with the discussion of the Lorentz group, which is probably one of the most, if not the most important group in physics, because it's the basis of special relativity, and henceforth, in some ways, the basis of quantum field theory and to some extent general relativity also. So just to recap a little bit, here's this thing called M, which is Minkowski space, which is a 4D space, okay? And 4-dimensional space, so locally it needs 4 coordinates. Usually they are the time coordinate and the 3 spatial coordinates. We call them x0. So let's say a particular point we call x, and x is usually given in terms of 4 coordinates with respect to a particular Lorentz frame, x0, x1, x2, x3. The first one is treated separately because of the metric. This is the time coordinate, x sub 0, and x1, x2, x3 are the 3 spatial coordinates, okay, of the subspace, which is 3-dimensional space. Now it's a metric space because it's given a metric. That means we can calculate distances between 2 different points in the space and so on and so forth. The metric is given by this 4x4 matrix, and the convention that we choose is -1, 1, 1, 1. All the rest are zeros like that. Okay, so that given a vector or a point in given vector or point in Minkowski space like that, where the coordinates are x mu, then the square of the length of this vector is then given in terms of the Minkowski metric to be eta mu nu, x mu, x nu. Okay, so basically then it is minus x0 squared plus x1 squared plus x2 squared plus x3 squared, like that. That's pretty obvious, okay? So remember, this is a metric, and this is a double index repeated, so that means both mu and nu are summed over. So after you're summed over, there's just a scalar, which is defined to be the square of the length of this particular vector. And here, notice that it's a non-positive definite metric because of the minus sign in here. This thing can turn out to be either positive, 0, or negative, okay? That distinguishes between the so-called space-like vectors, time-like vectors, and light-like vectors, and so on and so forth. If it's positive, that means the sum of these three is bigger than this. These are the spatial coordinates, so that vector is called space-like. Okay? If it's negative, that means the sum of these three is less than x sub 0 squared. It means the time component coordinate is bigger, so it's time-like vector. If this thing is exactly 0, which is totally possible because of the minus sign in here, then this thing is called a light-like vector. Okay? Light travels with the speed of light, so to speak, which is 1 in this case. Okay? Yeah?
For eta and mu, does it matter if mu is on the top?
Doesn't matter. Doesn't matter. In this case, doesn't matter. By general definition, if you're given a metric, which is not necessarily the Minkowski, the upper, you're talking about the upper indices, right? This guy is defined to be, this guy is regarded as a matrix, is defined to be the inverse of this matrix in here. So if you got a matrix like that, the inverse is apparently just itself. Okay? So in this particular case in here, whether you write it as eta, lower mu nu or upper mu nu is irrelevant. It's the same, in fact. But for the general case, the inverse of a metric is not the same as a metric itself. Okay? So this is the way it is usually written in the physics literature. This contravariant tensor is defined to be the inverse of this covariant tensor. Okay? The metric itself is always a covariant tensor with lower indices, okay, as originally defined. Okay, now we define this thing called a Lorentz group in 4 dimensions to be any transformation of vectors in Minkowski space which preserves the length of vectors themselves. Okay, so apparently lambda itself can be looked at as a 4x4 matrix. 4x4. So for this 4x4 matrix to be in the Lorentz group, it means that for any x in Minkowski space, lambda operating on x gives you another vector which has exactly the same length as the original vector. Okay? So if a big lambda satisfies this condition, then it's said to be a Lorentz transformation. Okay? In 4 dimensions with this metric, so we call it L4. And this condition can be translated, can be shown to be equivalent to this condition. I think it's like this. As we showed that last time, yes. So equivalently, if you're given a metric eta like this, you have any 4-dimensional matrix, 4x4 matrix lambda, which satisfies this condition, is a member of the Lorentz group. Okay. And now, from this condition in here, we derive 2 consequences. Number 1 is that the determinant of lambda, as in the case of 3-dimensional rotations, is plus or minus 1. It makes it sort of an orthogonal matrix. Okay. And then secondly, that the 0, 0 element itself, this one in here, the 0, 0 element itself, or the square of that, has to be bigger than or equal to 1, which means that the value of this element itself is either bigger than 1 or bigger than or equal to 1 or less than or equal to 1, because its square is always bigger than plus 1. Okay? So because of this fact, then we can divide up the whole Lorentz group into 4 disjoint pieces, so to speak. Okay? And the first one we call, there's a special name to that. I think this whole thing, L4, is also sometimes called O13. Okay, O means orthogonal. It kind of refers to this condition in here. And the 1 and 3 means that one of the coordinates is treated differently from the other three. Okay, that gives it what is called a Minkowski structure. Okay, okay, and I think that there's another name that we gave to this. I think, or maybe that's it. Or maybe that's it. So because of this condition, these two conditions in here, you can divide up the whole O13 or L4 into 4 disjoint pieces. The first one is what we call, sometimes write it like this. And we write it like this. The plus refers to the fact that the determinant is equal to +1. Up arrow means that lambda 0, 0 is bigger than or equal to 1. Okay? And the other 3 pieces would be equal to something that's derivable from, this is also, we sometimes also call this L sub 0. So there are 3 names given to it, okay? L sub 0. Oh, I'm sorry. L sub 0 is not this. L sub 0 is this. This is also called L sub 0, okay? A piece, which happens to be a subgroup because the identity is in that piece here, okay? Now, S in here is a spatial inversion. T in here is a time inversion. S and T is a combination of a spatial and time inversion. You flip time and you flip space. This is, you're flipping only the spatial coordinates. This is to change the sign only of the time coordinates. So we write this as L. You just change only the space part, so this is still upward pointing arrow. But then you change the spatial, then you change the sign of the determinant, so L minus. This is equal to L. You flip the time, so you change the sign of lambda 0, 0. Because it turns out that the determinant is -1. This one is in fact minus. And then finally, this one is, now you flip both space and time, so you don't change the time. You don't change the determinant itself, but then you certainly change the time, okay? So this is negative like that, okay? Now, S is what? You flip only the spatial inversion, so this is 1, -1, -1, -1, all zeros, okay? Now, sometimes this can also be taken to be the metric itself, all right? It really doesn't make any difference. As long as one of the coordinates is treated in the metric with the opposite sign than the rest of the coordinates. Time inversion is precisely this one in here, right? So the way we have written it, time inversion is just eta. I won't even bother writing it down because you see that only the time component is changed in sign, whereas the spatial components remain the same, okay? And ST is what? ST, you flip both the space and time. If you flip both the space and time, then you just get -1 times the identity matrix, okay? Flip both space and time, so you end up with something like this, okay? Or in other words, just -1 times the identity matrix, okay? And later on, we will show that actually all these are actually disjoint pieces, okay? This one itself is a subgroup, okay? Because you can show that it's definitely a subset. It's just definitely a subset of L4. It's a subgroup because the closure of the multiplication and the identity definitely belongs there. So in fact, it is a group. And so it's a subgroup. But none of the others are subgroups. They're subsets. But none of the others are subgroups for the simple reason that the identity doesn't sit inside of any one of those other 3, okay? But the 4 together form disjoint pieces, so you can think of the whole Lorentz group as being made up of 4 pieces like that. Oh, so disjoint, where the intersection of any piece with another one is equal to 0, okay? Okay? And now one of the exercises asks you to show that not only is this a subgroup, but it's a normal subgroup also. In other words, it's an invariant subgroup, which means that if you take anything in L plus, in this guy in here, And if you multiply it by G inverse on one side and G on the other side, where G is anything within the entire L4, okay, then this remains something inside of this subgroup. So in that makes it an invariant subgroup. So if it's an invariant subgroup, then that allows us to form a quotient group, okay? That allows us to form a quotient group, which is the L sub, which is L4 divided by L sub 0. In other words, this whole thing divided by this, or you can write it like this, L4 is O13 divided by SO13 outward pointing arrow, okay? That actually gives you these four things, each one of them regarded as a group element, okay? So that this thing is the identity element inside of this quotient group. And then you can make up a multiplication table which multiplies this thing by that thing by that thing by that, giving you things again inside of this group, okay? So the quotient group just consists of these four elements, each one of which, in terms of the original Lorentz group, is actually either a subset or a subgroup or whatever, okay? So in other words, we write that this quotient group consists of these four elements, like that. But this one is the identity element, all right? So that gives kind of like one aspect of the topological structure of the Lorentz group. Another fact which we're going to come back later to refer to is that unlike the SON groups, the SON groups are compact groups, but the Lorentz group is a non-compact group, okay? That has a very important consequence also, okay? Compact group generally means that in terms of the way that we are discussing things, that, you know, a Lie group, this is a Lie group obviously because it depends on the parameters specifying the group elements. The parameters form a continuous range of values. That's what makes this a Lie group. In other words, it's a differentiable manifold. But as we'll see later, the Lorentz group is a non-compact group because one of the variables does not have a finite range, okay? If you just think of Lorentz transformations, for example, Lorentz boosts, for example, the kind that you usually use in special relativistic physics, where the parameter is just the velocity of one frame relative to another frame. That velocity can be anything, okay? So the velocity itself can be regarded as a parameter of this group, okay, describing the so-called Lorentz boost, because that particular one is, the velocity can be from minus infinity to infinity. If you think of it as a velocity along a certain direction, obviously is a non-compact set with a whole number line, okay, so to speak. So that makes this a non-compact group, and so topologically, so that's very interesting, right? So it's a Lie group, it's a differentiable manifold, it's non-compact. And later on that we're going to see that it's, well, as we see it, it's not a connected group. It's not a connected manifold. They're disjoint pieces. You cannot get from one piece to another through a continuous path inside a manifold. And finally, there's another important quantity, another important aspect. It's not simply connected either. I'll explain to you later on what that means. Yeah?
Isn't speed of light finite?
Huh?
You said the speed can be any value.
The speed can be, oh yeah, you're right. The speed of light is certainly finite, but there's a parameter which derives from that which is non-compact, as we'll show you. Okay, it is a non-compact group. Huh? It does not just depend on the speed of light. Let me see exactly how I can put it. It's a parameter which derives from V itself. Okay. And it is that parameter. It is that parameter. Okay? V itself can be at most C, right? But when V is equal to C, that makes this thing infinite.
Oh,
okay? Sorry about that. We have to get there. That's called gamma, yes, right. Gamma itself is the non-compact parameter. Okay? Good question. All right, now, all this is kind of, we have discussed this before already. I just want to mention this, sort of highlight these topological facts, okay? Disconnected, non-compact, and later on I'll show you that it's not simply connected. Not simply connected means something like this, that if you think of a certain space, okay, and if you think of a loop inside of that space, if that loop can be shrunk down to a point, then it's simply connected. If a particular loop cannot be shrunk down to a point, then it's not simply connected. Now, what we're going to show that a double loop, so to speak, can be shrunk down to a point. So in that sense, it's what's called doubly connected. So the Lorentz group is doubly connected, okay, which turns out also to be a very important topological fact also. It has a lot to do with the part of physics which has to do with intrinsic spin of any relativistic particle, okay? Of any particle which has spin, as a matter of fact. Okay, now, to study, to try to kind of see how this abstract description fits into the kind that you are more used to in physics, such as the Lorentz boost, for example, how the time and spatial coordinates are transformed into each other and so on and so forth. We have to develop some preliminaries, and we started to do that already. In particular, we introduced the space of 2x2 Hermitian matrices, and we showed that there's a one-to-one mapping between the space of 2x2 Hermitian matrices and Minkowski space itself. Okay? In the sense that every point in Minkowski space, every such vector in Minkowski space can be associated with a 2x2 Hermitian matrix. And conversely, every 2x2 Hermitian matrix can be associated with a particular vector in Minkowski space. Okay? And so there's a mapping, an isomorphism, in fact, between Minkowski space and the space of 2x2 Hermitian matrices. So remember, we call this mapping F. It goes from M to H2. H2 is the space of Hermitian matrices. Remember, Hermitian matrix is one where its Hermitian conjugate is equal to itself. That's a Hermitian matrix. And Hermitian conjugate is the complex conjugated transpose of a matrix. Okay? So now, so F of some particular vector, x0, x1, x2, x3, means F acting on this, then we've wrote this down already, produces this particular Hermitian matrix x0 plus x3, x0 minus x3, x1 minus I, x2, x1 plus I, x2, like so. Okay? And conversely, there's an exercise which show that given any Hermitian matrix 2 by 2, and it must be of this form, where A and B are real numbers and C is a complex number, okay? So that this is Hermitian, so that you can see clearly that when you transpose it and then take the complex conjugate, it's exactly the same thing as itself. That makes it a Hermitian matrix, okay? In other words, the Hermitian conjugate, which is usually written as H dagger is equal to H itself. Okay? Now, this is a very interesting association, because if you look at four very special vectors, 1, 0, 0, 0, okay? This is the one which is apparently pointed along the time axis. And then we call this E sub 0. E1 is the one which is pointed along the x-axis. E2 is the one which pointed along the y-axis. And finally, E3 is the one which is pointed along the z-axis, like that. Okay? Then using this mapping in here, we saw that using this mapping, these four basis vectors, and of course these four can be thought of as the four axes in the four-dimensional Minkowski space, right? So they definitely form a basis set, okay? Just like our unit x-axis, unit y-axis, unit z-axis. Now this is unit t-axis, unit time axis also, okay? And we see that this one maps to the identity matrix itself. 2 by 2 identity matrix, definitely Hermitian, okay? This one takes us to something that we call the first component of the Pauli spin matrix, which is like that. This one takes us to the second Pauli matrix, or the y component of the Pauli matrix. It's very straightforward to take it from here, okay? And then finally, this one takes it to the third component of the Pauli matrix, which looks like that, okay? Now, because of this association, any Minkowski vector can be written as a linear combination of these, right? So in fact, any Minkowski vector can be written as x0, e0 plus x1, e1 plus x2, e2 plus x3, e3. In other words, it's x mu, e mu. Very plainly, okay? And so because of these associations, these four things can also be regarded as basis vectors in the space of 2 by 2 Hermitian matrices, right? So any, so the space of 2 by 2 Hermitian matrices can be thought of as a vector space of dimension 4 because it has the maximal independent set has 4 vectors in it. And these can be thought of as the basis elements. So any 2 by 2 Hermitian matrix can be written as x sub 0 sigma sub 0 plus x1 sigma 1 plus x2 sigma 2 plus x3 sigma 3. Now the difference between these two equations is that these guys, each of E0, E1, E2, E3 are themselves 4-dimensional vectors in Minkowski space. These guys are 2 by 2 Hermitian matrices, so that the linear combination of 2 by 2 Hermitian matrices is also a 2 by 2 Hermitian matrix like that. Okay? Yeah?
Can you repeat that one?
The last sentence? The difference between these two equations is that whereas these, E1, E2, E3, and E0 are basis vectors in Minkowski space, 4-dimensional space. Sigma 0, sigma 1, sigma 2, sigma 3, they themselves are not Minkowski vectors. They themselves are 2 by 2 Hermitian matrices. But there's this one-to-one correspondence between them, you see. And so the space of 2 by 2 Hermitian matrices is said to have a linear structure also because it is a vector space, okay? And so any Hermitian vector space can be written as a linear combination of these sigmas in here. And so each of these can again be thought of as a vector, quote unquote, whose components are exactly the same as the original components in the Minkowski space vectors. Yeah?
Are the components complex numbers?
No, real vector space. Real vector, that's important. Because in Minkowski space, all these are real numbers, okay? All the local coordinates in Minkowski space are real numbers. But the entries of the Hermitian matrices are complex. Okay? But the entries of the Hermitian matrices are complex. So it throws you off, right, somewhat. It's a little confusing also. But in mathematics, it's always important to realize that there are two different things which look very different from each other, but in fact there's an isomorphic relationship between them. Okay? On the one hand, you have Minkowski space, 4-dimensional vector space. On the other hand, you have the space of 2 by 2 Hermitian matrices. The things themselves are very different. But there's an isomorphic relationship between the things in one set and the things in another set. Okay? And consequently, each one of them can then be thought of as a linear vector space. Okay? You can certainly think of adding together those sigma matrices and so on and so forth. Okay? The sum of any two Hermitian matrices is also a Hermitian matrix. Hermitian matrix multiplied by any real numbers, definitely a Hermitian matrix also, 2 by 2. Okay? And so on and so forth. Okay? Now, there's also one very, very interesting fact that if you take this any general vector in here, we've already seen that the square of the length of that vector is given by this quantity, right? Which is this thing in here, right? Okay, that's the square of the length of any vector in Minkowski space. Now, let's think of calculating the determinant of this thing in here. Calculate the determinant of this thing in here. What do you get? The determinant of f of x. Okay? Think of calculating that. F of x is a 2 by 2 Hermitian matrix. In fact, it's this one in here. So calculate the determinant of that. What do you get? You get x sub 0 square minus x3 square minus x minus I x x1 minus I x2 times x1 plus I x2. Okay? It's this times that minus this times that. Okay? But what is that? That is x1 squared plus x2 squared. That's these are complex conjugate numbers, right? So number times its complex conjugate is equal to the square of its absolute value, which is the square of the real part plus the square of the imaginary part. Okay? But you put it all together, what is this equal to? Minus signs in here, so this is equal to minus of x sub 0 squared, minus and minus, plus x1 squared plus x2 squared plus x3 squared. And that's precisely equal to minus the square of the length of the vector. Okay? So when you do this mapping in here, you take the determinant of this, it's precisely equal to minus the square of the length of the original Minkowski vector. Now that fact is also very important. Okay? And we're going to make use of that. Now, before I go on, since we have introduced these sigma matrices, how many of you have seen these sigma matrices? I've asked you before. Definitely those of you who have taken a quantum mechanics 402 will have seen this, okay? If not, then it's okay. Just treat it as some new objects that we are introducing at this point. But in quantum mechanics, these are the equivalent of angular momentum operators in a two-dimensional spin system, okay? So the electron spin is 1/2, so it has eigenvalues of L sub z equal to +1 or -1. That's precisely why this guy has, this 1 and -1, which indicates that the z component of the spin can either be +1/2 h or -1/2 h for an electron. And so sigma 1, sigma 2, sigma 3 can be thought of as angular momentum operators in two-dimensional spin space. All right? The ordinary orbital angular momentum are 3 by 3 matrices, as you saw in the last problem in the exam, in the midterm exam. But again, in quantum mechanics, we talk about abstract spaces, so that for spin systems, we talk about two-dimensional spaces. So you need the two-dimensional representation of angular momentum vectors to operate on those two-dimensional vectors, which turn out to be precisely the sigma matrices. They're also called, they are these matrices. Pauli was the one who first used them, so they're called Pauli matrices. Okay? I don't know if Pauli realized that this particular kind of relationship between Minkowski space vectors and so on and so forth. But he was the first one because he only introduced sigma 1, sigma 2, sigma 3. Those are the operators in non-relativistic physics. You don't deal with mixing the space and time components in non-relativistic physics. Okay? But it's important for us to remember that if you bring in a time component, there's this further identification that the time axis is mapped onto the identity matrix, which it's always very interesting also in a way. Okay? Now, since I have introduced the Pauli spin matrices, they are the two-dimensional representations of the angular momentum vectors for the group SO3. SO3, okay? Two-dimensional representation of SO3. That's entirely possible, okay? There are three-dimensional representations, four-dimensional representations, five-dimensional, and so on and so forth. Since the Pauli matrices are so important in quantum mechanics, you use them all the time in doing calculations in quantum mechanics. There are some relationships among them which are very important, which I've asked you to prove in one of the exercises. It's a neat exercise, doing commutation relations between those Pauli matrices and so on and so forth. But I won't prove in detail. Let me just quote them in here. First of all, you see, each one is definitely a Hermitian matrix, so therefore it is equal to its own Hermitian conjugate. Okay. There's another important fact. That is, if you limit yourself to E1, E2, E3, okay, for each one of them, the trace is equal to 0. The trace is the sum of the diagonal elements. Not this one. The trace of this is 2. Okay, but you see, if you limit yourself to the spatial components, sigma 1, sigma 2, sigma 3, the trace is equal to 0. Special property of the Pauli matrices. For I is equal to 1, 2, 3. Actually, for 0 also in this case, but definitely for the i's. Okay, so all these relationships that I'm writing down here are for I is equal to 1, 2, 3, definitely. And the first one definitely is true for I is equal to 0 also, okay? Very interesting, anti-commutation property, okay? Sigma I, they don't commute, so sigma I times sigma j is not the same as sigma j times sigma I, but when you take this is called the anti-commutator, where you replace the minus sign by the plus sign. It's very important in quantum physics also, okay, the anti-commutator. It makes a difference between bosons and fermions, depending on what they satisfy commutation relations or anti-commutation relations, okay? Now, definitely since they are representations of the angular momentum, they have to satisfy the commutation relations also. That is obeyed by any angular momentum operator. Sigma, let me write it like this. The way I wrote it in the text is a sigma j, sigma k commutator. Now, that means sigma j, sigma k minus sigma k, sigma j. It's not equal to 0, but it's equal to 2i. This is a Levi-Civita symbol. J, K, L, sigma L. So that's the same commutation relations as the angular momentum operators, L1, L2, L3. Same thing satisfied by sigma 1, sigma 2, sigma 3. Why? Because they are just different representations of the SO3 group, or the Lie algebra of SO3. Because of this commutation relation, we have this, we have the product in one order can be expressed in terms of the product of the other order. So sigma j k, or maybe not necessarily. You can anyway. You have you have this relationship, epsilon I j k l sigma l. Okay. Well, this first term obviously means the Kronecker delta sigma j k times the identity 2 by 2 matrix in here. Okay. So all of these are 2 by 2 matrices. So these are products of 2 by 2 matrices in here. Okay. So for example, you can think of the fact that sigma 2, sigma 3 would then be equal to 0 because it would be delta 2, 3. Sigma 2, sigma 3 would be equal to I sigma 3. Okay. Sorry, sigma 1. So it's 2, 3, jk, 2, 3, that the only one is 1 in here. Possibility. Okay. The sigma 2, sigma 3 is equal to I sigma 1, and so on and so forth. Okay? Now, then there's this one in here. Given any two three-dimensional vectors A and B, this can be shown to be equal to A dot B. A very, very useful relationship in doing quantum mechanical calculations. A cross B dotted with sigma. Now, what is meant by this? You have to treat this carefully. A is just an ordinary vector, so it has 3 components, A1, A2, A3. Similarly, B has 3 components, B1, B2, B3. The meaning of this symbol is this. It's A1 times sigma 1 plus A2 times sigma 2 plus A3 times sigma 3. Okay, ordinary scale product. So that makes the product what? A 2 by 2 Hermitian matrix. Okay? Is the sum of 3 2 by 2 Hermitian matrices. Okay? So similarly, this is another 2 by 2 Hermitian matrix, and you have the product of 2 by 2 Hermitian matrices. It gives you another Hermitian matrix. Okay? Oh, wait a second. Maybe not. The product of 2 by 2 Hermitian matrices. Is it a Hermitian matrix? Oh. Let's try. So let's say if A and B are both Hermitian, so A is equal to A dagger, B is equal to B dagger. Is A B Hermitian? The product of 2 by 2 Hermitian matrices. A B dagger is equal to B dagger, A dagger, which is equal to BA. Oh, not necessarily. So AB dagger is not necessarily equal to AB. So even if A and B are separately Hermitian matrices, the product is not necessarily a Hermitian matrix. Okay, so you have to be careful about that. So that either side doesn't have to be a Hermitian matrix, although it's definitely a 2 by 2 matrix. Okay. Sometimes a simple test you can carry out to see whether or not something is true. So what this means is this is A1 B1 plus A2 B2 plus A3 B3. But what this means is that this number times the identity 2 by 2 matrix. That's what it means. Okay. And similarly, this A type, if A and B are each 3 vectors, then A cross B is treated as a 3 vector. Okay. So again, you have the 3 components of this 3 vector dotted with the 3 components of sigma. So you have the first component of A cross B times sigma 1 plus the second component of A cross B times sigma 2 plus the third component of A cross B times sigma 3. So at least the whole equation makes sense, but it's also true. Okay. And part of the exercises ask you to prove that. The reason why I ask you to go through that is that all these are very important facts in quantum mechanical calculations using spin matrices. Okay. Finally, there is this one. E to the I times some real number times sigma j. So sigma j is a 2 by 2 matrix. So the whole thing is a 2 by 2 matrix. So so this is E to the 2 by 2 matrix, which is also a 2 by 2 matrix. Always exponential of a matrix always converges. Okay. And I want to write this. Now this looks something like an ordinary complex number, but it is not, because this guy is here 2 by 2 matrix. But the formula looks something like the formula E to the I theta is equal to cosine theta plus I sine theta. Okay. With the addition of, with the difference that the obviously the sigma matrices has to sneak in someplace. Okay. Now, as before, cosine theta is a number because theta is a number in here. So this is interpreted to be this number times the identity 2 by 2 matrix. Okay. And of course, this is a 2 by 2 matrix because sigma j is a 2 by 2 matrix. Okay.
So cosine theta doesn't have to be.
Cosine theta is just a number. As I said, this is to be interpreted as cosine theta times the identity 2 by 2 matrix.
I mean, theta is not multiplied by sigma j.
No. No. It's multiplied by the identity matrix. Because the identity matrix is also a basis vector in the space of 2 by 2 Hermitian matrices. So you see, this tells you that actually this whole thing is Hermitian. This whole thing is Hermitian, okay? And so 1 is definitely Hermitian, you know, and so each of the sigma j's is Hermitian. So that makes the whole thing a Hermitian matrix also, okay? Now that also is a very important identity because, again, in quantum mechanical calculations, very often you're required to calculate the exponential of the sigma matrices. And this is it. Okay. All right. It'll be a lot of fun trying to prove these. Okay. Let's go back to our development. Next thing is a very, very important thing. We are going to introduce a group homomorphism between 2 groups, one of which is obviously the Lorentz group. The other one is, guess what? So some group of 2 by 2 matrices. Okay. As you see, the group of 2 by 2 matrices is named by this, SL2C. S means that the determinant is equal to +1. 2, L means linear. Obviously, it's a 2 by 2 matrix, so it's treated as a linear operator. C is that this is a matrix of complex numbers in general. Okay. So when you have a 2 by 2 matrix, so there are 4 complex numbers in there, but it's kind of constrained by one relation, which is that the determinant has to be equal to +1. So there are actually only 3 independent real numbers in this group. It's called the special linear group of 2 by 2 matrices of complex numbers. There is an extremely important and interesting homomorphism between SL2C and the Lorentz group. The Lorentz group that we have been discussing up to now. It's not surprising because we have this relationship, this isomorphism between 2 by 2 Hermitian matrices on the one hand and the Lorentz vectors and the Minkowski vectors on the other. Okay? So it's not surprising then to see some kind of mapping between some set of 2 by 2 matrices and the transformations of the 4 vectors which preserves length. Okay? This group homomorphism we call phi. Okay? Now remember what a group homomorphism is. It has to satisfy the most important property. I asked you about that in the test, which is the preservation of multiplication. That means if G1, G2 are both in SL2C, then phi of the product G1, G2 has to be equal to phi of G1 times phi of G2. Okay? This is the most important homomorphism property. The other is that, of course, this does not necessarily have to be an isomorphism. Okay? And homomorphism is actually between 2 groups. Okay? Now, we know that this is a group already. In fact, one of the first exercises is to ask you to show that this is in fact a group. The set of transformations which preserves lengths is in fact a group, okay? Which I leave it up to you. Now let me very quickly show you why this itself is a group also. Okay? In other words, if G1 and G2 are both in SL2C, then how about G1 times G2? Is it in S2L2C also? 2 by 1, let's say 1, 2, let's say your G1, let's say is equal to 1, 2 by 2 matrix, and the determinant is equal to 1, okay? Because it's in S, determinant G1 is equal to 1. Special is determinant equal to +1. G2 is also another 2 by 2 matrix, such that its determinant is also equal to 1. So now let's think of the product of these 2 matrices. It's definitely a 2 by 2 complex matrix also, right? Because it's a product of 2 by 2 complex matrices. In general, the product is also a 2 by 2 complex matrix. What's its determinant? 1. Why? Because determinant G1, G2 is the determinant of G1 times the determinant of G2. Each of those is equal to +1, so therefore the product is equal to 1. So this proves the most important property, the closure property of a group. That means if 2 things in here, if 2 things belong in here, then the product of those 2 things also belong in here. Okay. The identity is definitely that. The identity is a 2 by 2 matrix, and the determinant of the identity matrix is equal to +1 also. Even though all the matrix elements are real, it's okay because the real number is just a very special complex number with imaginary part equal to 0. That's all. Okay. So the real numbers actually form a subset of the imaginary numbers. In fact, just the real line, okay? Whereas the imaginary numbers is the whole plane. The real number is just a line, okay? Definitely a subset. This guy, has an inverse. Why is it obvious that it has an inverse? The determinant is not 0, okay? So the determinant is +1, it must have an inverse, okay? And that just about does it, okay? That this is a group itself. Now, what exactly is that homomorphism? That's what we are trying to write down. What exactly is that homomorphism, okay? In other words, the idea is this, right? Instead of dealing with 4x4 matrices, which are the Lorentz transformation themselves, sometimes, a lot of times, in fact, it's easier to deal with 2x2 matrices. Okay? And the calculations of products and so on is easier to calculate. Okay? And it's in fact a very fortunate fact that we do have this homomorphism, which I'm about to write down, which preserves the multiplication. Okay? But the homomorphism is a little bit convoluted. So let me take you through it step by step. Let me leave those things there. Let me, first of all, actually the figures in the notes, so you don't have to copy it down. Let me, as mathematicians usually like to do, they put down some kind of so-called commutative diagram like this. I don't know what this is. So I have already a mapping that I have established between M and H2, okay? This is a 1-to-1, so therefore it has an inverse. So the inverse mapping takes you from H2 to M, which I'm simply going to call it the inverse in here, like so, okay? Now, obviously, some Lorentz transformation will take you from M to M, okay? And let's say that this is something in this group, some Lorentz transformation in this group. And we will define that, and we will call that something to be the image of phi of some G in SL2C, okay? So I'm going to write phi G in here, which is actually a member of the Lorentz group. And here I'm going to write G in here. G is a G definitely maps something in H2 to something in H2. This G is itself a 2x2 matrix. So you can think of G multiplying by something in H2. And through this homomorphism, phi, I take G to phi G. Okay? I take phi to phi G, like that. And phi G is in L4. Okay, remember that. Phi G is in L4. Okay? So that's why I write phi G is in L4. What is G in? What is G? G is in SL2C. Okay? This is the belonging to symbol written kind of backwards. I hope you understand what I mean. Okay? Okay, just keep this in mind with all these things, okay? So I'm going to write the homomorphism like this. Well, in order to establish the homomorphism, I have to do something like this. Given a particular G in here, phi G becomes a Lorentz transformation. So I must tell how that phi G transforms a particular Lorentz vector, a Minkowski vector, okay? In other words, given G, I'm going to have phi G, which is supposed to act on X inside of M. And if I know what the action of this on X is, then I will have specified the action of the homomorphism, phi on SL2C. Okay, in other words, I must tell how this thing in here, which is supposed to be a thing in L4, transforms this Minkowski vector. Is that okay so far? Okay. So since this thing is supposed to be a Minkowski vector, right, I can use F to map this thing to where? to H2. In other words, given a G, I have to tell which 2 by 2 Hermitian matrix it is on this side. Okay? And the answer is this. Now I have to show this, okay? But this defines the homomorphism for you. What are you given? You're given phi, okay? And you're supposed to know how phi acts on, what the result is, phi acting on G. Phi acting on G gives you a Lorentz transformation. Therefore, in order to specify that Lorentz transformation, I must be able to tell how that Lorentz transformation acts on any Minkowski vector, okay? It's supposed to be a Minkowski vector, so therefore I can use F to transform that to a 2 by 2 Hermitian matrix. But Fx is a 2 by 2 Hermitian matrix, okay? And so the first important thing I have to prove is that if Fx is a 2 by 2 Hermitian matrix and G is any SL2C matrix, this whole thing is a 2 by 2 Hermitian matrix also. Okay? And if that gets established, then I have my homomorphism. It's a little convoluted, right? But you have to constantly keep in mind this little diagram like this, and the two mappings, one is the F and the other is the group homomorphism. This is simply a vector space isomorphism. This is a homomorphism. That's one-to-one. That's not necessarily one-to-one. That's just a homomorphism. Okay? But it does have to preserve this multiplication product, which I still have to show you. In other words, I have to show you that this is a well-defined statement. Okay? I have to show you this is a well-defined statement. So therefore, let me try to break it down and step by step. Try to prove all those different things which I just mentioned, which have to be proved. Okay? First thing I want to prove is that if Fx is a 2 by 2 Hermitian, then this product is also a 2 by 2 Hermitian. Otherwise, the thing is not well defined. Yeah.
Can you explain how an element G in SL2C takes H2 to H2?
This is to be proved. To be proved. Okay. 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 It will come. All right. But first, let me prove that if Fx is a 2 by 2 Hermitian, then this product is also a 2 by 2 Hermitian, right? This product is also a 2 by 2 Hermitian. To prove something is Hermitian, you prove that what? It is equal to its own Hermitian conjugate. Okay? In other words, you have to calculate G Fx G inverse the Hermitian conjugate. Okay? And see whether or not it is equal to itself. Okay? Remember, this itself is in H2, so that one is Hermitian. That one is Hermitian. But G is not necessarily Hermitian. Okay? G itself is not necessarily Hermitian. But you do require that its determinant is equal to +1. Okay? All right, let's see. Well, obviously, this is a 2 by 2 matrix. There's no doubt about that. We just have to prove that it is Hermitian. And so now, I don't think I have demonstrated. Let me see. Oh, sorry. I'm not proving that it's Hermitian. I'm proving that it's in SL2C. I'm sorry. Okay. Because all I want is that it is in SL2C, so that I can map it using this homomorphism. I have to prove that. I'm sorry. I created this confusion at first. Prove that if Fx is 2 by 2 Hermitian, then G fx G inverse is in SL2C. If f and G in SL2C, right? G is in SL2C. You see, the mapping under f of anything sorry. This is, fg itself has to be in, let's see. Did I make another mistake somewhere? I think I'm fine. I think I'm fine. Yeah, I think I'm fine. So the idea is this: f phi g is a Lorentz. Phi g itself is in SL2C. So phi g is in L4. L4 x on x. So this gives you another x in here. But so f maps x to some. Let's see. F maps x to some SL2C. Oh, actually, I do have to prove that. Oh, I'm sorry. Actually, I do have to prove that this is in H2. I'm sorry. I'll go back to my. This has to be in H2.
Oh, Dr.
Yeah,
Isn't
yeah.
that supposed to be G dagger instead of
Oh, G dagger. Yeah, G dagger. That's the mistake I made. I copied it wrong. G dagger. I have to be very careful. These are not unitary, so therefore G dagger is not equal to G inverse. Okay. Now I'm okay. I think now I'm okay. Now I am okay. So to prove that this is in H2, I have to prove that the Hermitian conjugate of this is equal to itself, right? But you know that there's this famous, I don't know if you can prove this pretty easily, that the Hermitian conjugate of the product of A and B in this order is equal to B dagger, A dagger, just like the inverse, okay? So therefore, the Hermitian conjugate of this must be equal to G dagger, Fx dagger, G dagger dagger, okay? Oh, G dagger. Sorry. Wow, I'm really making mistakes in here. This is G dagger dagger first. G dagger dagger in reverse order, right? So this whole thing dagger is G dagger dagger times F dagger times G dagger, like that. Okay? But G dagger dagger is just G. Okay? You can prove that easily also. The Hermitian conjugate of the Hermitian conjugate is itself. Okay? But F is Hermitian, so therefore F dagger is just equal to F. And then you finally have G dagger. So the dagger of G Fx G dagger is equal to itself. So therefore the result is in H2. So therefore we have proved that this, if G is in SL2C, then in fact we didn't even need to make use of the fact that, well, certainly it's true that you have what we have in it. G is in, we're going to need the fact that G is in SL2C a little bit later on, okay? But so far we just need the fact that G is a 2 by 2 matrix, okay? And the fact that F is 2 by 2 Hermitian, okay? So we have proved the first step, which makes this part of the definition sensible, okay? So that this is in fact something in H2, which ought to be something in the image of this mapping F in here, okay? Then the next thing that we need to prove is that phi of G is in fact in L4, right? So we have to prove this as defined, phi of G, as defined like this, phi of G is in fact in L4, okay? How do you prove that phi of G is in L4? You make use of this fact, that this phi of G produces a Lorentz transformation which keeps the length of a Minkowski vector invariant. Okay? So that's the definition of a Lorentz transformation. But the length of a Minkowski vector is given by what? Or the negative of the length of a Minkowski vector is given by the determinant of this guy in here. Okay? So we have to check that the determinant of this guy. No, sorry, the determinant of this guy. The determinant of this guy is in fact invariant. Okay? So let's calculate the determinant let's calculate the determinant of this thing in here, right? Okay. So let's calculate the determinant of this thing in here. We know that phi of g is so we know that this is this thing in here, which is at the same time equal to this length is in fact equal to the determinant, or the negative of this length squared is equal to the determinant of this thing in here. So we're going to write this as equal to minus the determinant of what? By definition, f of phi of g acting on x. Is that confusing enough? Okay. You see, f of phi of g acting on x is by definition equal to that thing on the right-hand side. Okay? But that thing on the right-hand side is a 2 by 2 Hermitian matrix, as we have just seen. So therefore, by this mapping, it corresponds to some Minkowski vector in here. Okay? And the length of the Minkowski vector squared is precisely equal to the determinant of this matrix in here. Okay? So we have to calculate the determinant of this matrix in here. Okay? You see how it goes? So the determinant of this matrix in here, you see, this is what? By definition, this is equal to G fx G dagger. Okay? So I have to calculate the determinant of the product of these three matrices, which is just equal to the product of the determinants, okay, by famous equality of determinants. So it's minus determinant G times determinant fx times determinant of G dagger. Okay? Which is equal to minus determinant G. Let me write it like this. Each of these are just numbers, being a determinant. So this is determinant of G dagger, and this is determinant of fx. Right? But what is the determinant of fx? The determinant of fx, this part, is equal to minus x squared. Right? Just showing that. Okay. I know what the determinant of G is. What is the determinant of G? Plus 1, why? Because this is SL2C. But then the next question is, what's the determinant of G dagger? Also equal to plus 1. Why? G dagger is not equal to G. Because G is in SL2C, it's not necessarily Hermitian, right? But how is the determinant of G dagger related to the determinant of G?
You could multiply something within SL2C by G to get something within SL2C.
Well, let me give you an SL2C. Let me just simply write it like this: A, B, C, D in SL2C, like that. Okay. So the determinant is equal to AD minus BC. Right? Is that right? Determinant is AD minus BC. So let me say G is equal to that. So determinant G is equal to this. So let me write G dagger. How do you write that?
Conjugate of A, conjugate.
Transpose and then complex conjugated, right? So first transpose it first. All right? And then complex conjugate. Okay? So what's the determinant G dagger? A complex, bar means complex conjugated. Sometimes you use star. Let me use bar, okay? Because that's the way it's used in the text. So it's A complex conjugated, D complex conjugated minus B complex conjugated. Now, how are the two related to each other? One's a complex conjugate of the other. So, where was I? So this is apparently equal to the complex conjugate of determinant G. But you know determinant G is equal to plus 1, so therefore the complex conjugate is also equal to plus 1. So in fact, the complex, well, in fact, those two factors just contribute to a factor of plus 1. So it's minus, so it's plus 1 times plus 1, okay? So it's plus 1. So it's minus minus x squared, so the whole thing is just equal to x squared. So what have I shown? I've shown that the length of the transformed vector is equal to the length of the original vector. Okay? And so therefore, so this part of it makes sense. Okay? So this part of it makes sense that this phi of G is in fact a Lorentz transformation because it preserves the length of a vector x. Okay? So I've proved that. Now I have something else to prove. What do I have to prove? I have to prove that it actually satisfies this property, that this particular homomorphism defined by this way preserves the multiplication. Okay? So now I need to prove this. That is in fact the main homomorphism property. Okay? So for G1, G2, both in SL2C, I have to show that phi of G1, G2 is equal to phi of G1 times phi of G2. Now how do I prove that? Okay. This is a group, so G1 times G2 is something in here also. So this is phi mapping something in SL2C. It should produce something in the Lorentz group. Okay. And that particular Lorentz transformation is supposed to be equal to this Lorentz transformation times this Lorentz transformation. That's what I want to show. Okay. So let me start off this way. I start from the left-hand side. Do you want to take a break first? Yes? Okay, go ahead. We'll take a 5-minute break, okay? I think we're getting tired. To prove this next part, which is to prove the main homomorphism property, let me just rewrite this equation slightly differently, okay? So this equation is exactly the same as phi g operating on x is the inverse map of f acting on G fx G dagger. Is that okay? It's exactly the same way of writing it, okay? In other words, if I multiply on the left by f inverse, that makes this the identity operator, so therefore this is equal to f inverse acting on this. You see, f inverse takes you from M back to H2, okay? So this thing itself is in H2, okay? So F inverse takes you from H2 back to M, which is a Minkowski vector, which is precisely the result of some Lorentz transformation acting on a Minkowski vector, okay? So let's start from the left-hand side of this equation, which is phi of G1, G2 acting on X, okay? To prove that these two things are equal to each other, I need to let them act on the same X, right? And see if they produce the results. Each of these is supposed to be a Lorentz transformation, right? So I write phi of G1, G2 acting on X. Is this notation okay? Then I use this formula is F inverse of G1, G2. That replaces whatever G we have in here, Fx. Let me do this very carefully. G1, G2 dagger. Okay? But immediately I'm going to change G1, G2 dagger into G2 dagger times G1 dagger. All right? So this becomes G2 dagger, G1 dagger. And immediately I'm going to group these things. Each of these things is a 2 by 2 matrix. So they have to be multiplied in that order, okay? So I'm going to group it like this. Okay? But what is that? According to this, F of G2, let me write it first, right? So according to this definition in here, that's F acting on phi of G2 acting on X. Is that okay? Yep. Okay. F of phi of G2 acting on X. And now I'm going to use this equation once more. Okay? Because this is in what? This is something in H2. Okay? And so therefore, it plays the role of whatever this is in here, something in H2. And then I have some G and G dagger to the right. So this time I have G1 and G1 dagger to the right. You see the relationship, okay? And so therefore, I can write this as F inverse of F of what now? Phi of G1, thank you. F of phi of G1, and then what? Of just phi of G2. Is that right? Of just phi of G2. Is that right? Is that okay? G1 acting on oh no. Yeah. Let's see. Yeah, that's fine. That's fine. Yeah, that's fine. Yeah. G1 acting on F of something. This plays a role of X, right? Yeah. G1 acting on F something times G dagger is equal to F of phi of G1 times that something. Okay, so we have that. Okay. Oh well. But what do we have? F inverse and F. F inverse and F gives. That's it. Okay. So that gives phi of G1 times phi of G2 times X. So we have proven what we wanted. Phi of G1, G2 is equal to phi of G1 times phi of G2. That's the homomorphism property. So therefore, up to this point, we have just proved that this is well defined. Okay, it makes sense. This definition makes sense. It is a homomorphism. It's a homomorphism from this group to this group. Okay, that's what we have proven so far. Now, next we're going to show a very important thing, that this homomorphism is not one-to-one. It's not one-to-one. In fact, it's two-to-one. Because it maps two different things in SL2C to the same thing in L4. And that's relatively simple to prove. So, so what we are trying to prove is that G and minus G both map to the same thing under this group homomorphism. G and minus G are definitely different matrices in SL2C, but they both map to the same thing under the group homomorphism. Why? Because if you use Fg to act on X, by definition, this definition, in fact, it is equal to F inverse of G Fx G dagger. So I'm going to do this trick, right? I'm going to multiply this thing by 2 factors of minus 1. Doesn't change it, which is a plus 1, okay? I'm going to stick one of the minus 1s in here and one of the minus 1s in here, okay? So this is equal to minus G Fx minus G dagger. Minus G dagger is exactly the same as minus 1 times the G dagger. Okay? All right. And so by this definition again, what is this equal to? Phi of minus G acting on X. Now remember, this is for any X in Minkowski space. So therefore, phi of G and phi of minus G both produce the same Lorentz transformation. Okay. You can draw a diagram like this. So this is SL2C. This is L4. It's a group homomorphism, so therefore the identity goes to the identity here. Okay. But for anything that's not the identity, you have 2 different group elements in there, G and minus G. And according to this homomorphism, they both map to the same thing in L4 under phi, like so. Okay? This, in fact, is a very important fact which relates to the property of double connectedness of the Lorentz group. Okay? SL2C itself is simply connected. Lorentz group is doubly connected. So this is, whatever it is, it's phi of G, but it's at the same time also equal to phi of minus G. Like so. Okay? So any Lorentz vector is a linear combination of the 4 basis vectors, right? E0, E1, E2, E3. And so therefore, to study this homomorphism, we're going to study the image under phi of certain vectors in here which acts on the 4 basis vectors in Minkowski space. Okay? So first of all, let us take a subgroup of SL2C. This is SL2C, which is quite a big group. There's a subgroup which is called SU2. Do you know what SU2 is? Special unitary group of 2 by 2 matrices. Matrices of complex elements. But it has to have determinant equal to +1, which obviously it has to be because it's a subgroup of SL2C. Okay? But in addition to that, these matrices are supposed to be unitary, which means that its Hermitian conjugate is equal to what? Its inverse, right? So a general thing in SL2C need not be unitary, but here we are considering a subgroup, okay? And you have to convince yourself that SU2 is, well, it's a group, therefore it's invertible, and so that's enough to see that this is a subgroup of this in here, because it has determinant +1, okay? Among all the SL2C matrices, there's a subgroup which consists of unitary matrices. Yeah?
Could you repeat the unitary definition?
Unitary matrix is when its inverse is equal to its Hermitian conjugate. Okay? So a unitary matrix. Unitary matrices are of fundamental importance in quantum mechanics because all the quantum mechanical transformations, are unitary transformations. In other words, unitarity is something that's a little bit more general than orthogonality. It's a rotation of complex vectors which preserves the length of complex vectors in a certain way. Okay? Do you know why SO matrices are a subset of unitary matrices? SO matrices are real matrices, right? And so therefore its complex conjugate is equal to itself because they are real. But what is the Hermitian conjugate of an SO matrix then? Complex conjugate of the transpose, right? But since the complex conjugate is equal to itself, it's just transpose. For a real matrix, the Hermitian conjugate is its transpose. So then the requirement of orthogonality is simply the transpose is equal to the inverse, right? So therefore, it's a generalization to unitary matrices is when the inverse is equal to Hermitian conjugate instead of just the transpose. Because if it's a real, the Hermitian conjugate is just equal to the transpose. Okay? So therefore, the unitary matrices are supposed to be understood as a generalization of the orthogonal matrices when extended to complex space, okay? How the matrices act on complex vectors instead of just real vectors, okay? Anyway, we look at the subgroup, which is SU2 of SL2C, and we would like to see the restriction of phi to this subgroup. This applies to the whole SL2C, right? Phi, but if we use the same action of phi and restrict it to this subgroup, and let's see what kind of action we get on the Minkowski vectors, okay? So let's say for any G in SU2, since it's unitary, G times G Hermitian conjugate must equal to 1 because the Hermitian conjugate is equal to its inverse, okay? And obviously we also have determinant G is equal to +1. This is the unit matrix in here, +1. Now, let's look at this action on look at the action of phi of G on the four basis vectors, right? E sub 0. This is one vector, okay, which is which one? Like that, okay, and so on. Let's look at this one first, okay. Now, so let's see what happens if we use phi of G to act on E0. Use the definition here, okay? Phi of G act on E0 is equal to F inverse, same method here. G, F acting on E0, right? Times G dagger, right? But what is FE0? Remember, F takes you from Minkowski space vectors to the space of 2 by 2. If this is E sub 0, what is this? I just erased it. I'm sorry. Okay. Let me put it back, okay? Which is the identity matrix. Okay? Also, I might as well put it back. Fe1 is equal to sigma 1. First sigma matrix, Pauli matrix. Fe2 is equal to sigma 2. And Fe3 is equal to sigma 3. All these are 2 by 2 matrices, okay? Like that. Let's just focus on this one first. So this is the identity matrix, right? 2 by 2 identity matrix. So this gives me F inverse of GG dagger, right? Well, what's GG dagger? The identity matrix. The identity matrix. Oh, well, I wrote this as 1, but I also use E to write it in here. And what's that equal to? F inverse of the identity matrix. F inverse of the takes you from the identity matrix to E sub 0. Back to E sub 0, because F is an isomorphism. Okay? Now it's very interesting. If G is an SU2, the Lorentz transformation, which is obtained from phi of G, does not change the time axis. When it's acting on the time axis, it leaves it alone. It doesn't do anything to the time axis. E sub 0 is the time axis, remember? So if a transformation doesn't do anything to the time axis, what else is it left to do? Change the spatial, change the spatial axes. In other words, as we are going to see, we're going to see that that it's going to do something like an SO2, SO3 element. Okay, in other words, well, you see the connection, okay? But we have to prove one thing, that it leaves, when it's used, when the homomorphism restricted to SU2 acts on something in 1, 2, 3 space, it doesn't produce a time component. We have to show that also. When it acts on the time component, it leaves the time alone. But when it acts on the spatial components, we have to show that it stays within the spatial components. Then we will be sure that the restriction of phi restricted to SU2 is like a rotation. Okay? So next thing we're going to try to prove is, in fact, that. Okay? So, so we use the notation phi restricted to SU2. Okay? It's supposed to be something in the Lorentz transformations. We're going to show that the subset of the Lorentz transformations is, in fact, just the SO3 elements. Okay? We have shown already that it doesn't change the time axis. In other words, the time component doesn't get mixed in with any spatial components, which is what a Lorentz transformation usually does. Okay? Like you act on just a vector which acts along the time axis, the Lorentz boost would produce, it mixes the time and space components. And conversely, when you act on something which points only along the spatial direction by a Lorentz boost, it mixes in some time components also. Okay? We're trying to see that if you restrict this homomorphism to SU2, it doesn't do that. We have shown that it leaves the time axis alone. So therefore, we've got to show that when it's used to act on some vector that has 0 component along the time axis, then that subspace, the 3-dimensional spatial subspace, is invariant under this restricted homomorphism. Yeah?
What's a Lorentz boost again?
Huh?
A Lorentz boost?
Lorentz boost? The Lorentz boost is, let's say, in physics terms, when you have an ordinary inertial frame, okay, and then you observe physical phenomena with respect to this frame in here. You go to another frame, which is moving with respect to the first frame with some finite velocity, less than or equal to c, okay, as you said. Okay. then the physical phenomenon will be you know will be observed to the components. Okay, will be if you observe a time a vector which is only in this subspace. Okay, and then the components of the same thing. If you observe some flying object in here, okay, with respect to these two inertial frames, one of which is moving with a constant velocity relative to the other one, then it's found that the spatial components of this will depend on the time also, okay? And that's called a Lorentz boost. You boost it, and it's just like you boost it along a frame traveling with, you think of that's yourself here sitting down on Earth. Your twin is traveling in a rocket, which is flying away with some velocity, and so therefore he observes things with respect to a different frame, which is moving at a constant velocity relative to the first one, and so on. Are most of you familiar with this term, the Lorentz boost? Mm-hmm. That probably was first introduced to you in Physics 234, I guess. You talk about those those Lorentz transformations. You remember those Lorentz transformations? Yeah. In fact, I wrote that down already. That if you have x, y, z, t in one frame, and x prime, y prime, z prime, t prime in the other frame. Normally in classical mechanics, t is like not a component. We just, t is just a parameter. But in relativity, time is a component. So this is a 4 vector in here. Okay. You find that if one frame is boosted along the x direction, then x prime would be something like, I don't recall this, it would be something like x minus v t divided by 1 minus v squared over c squared, something like that, right? Okay? If the boost is along the x direction, y is the same as y prime, z is the same as t prime. But t prime is equal to some linear combination of is it like that?
Yes.
Okay, something like that. Okay, but have you seen this? But if C is, I'm going to show you how later on how our formulation leads to exactly these formulas, the Lorentz transformation formulas. Okay. That's a Lorentz transformation. That's a transformation given coming from a Lorentz boost along the x direction. But you can have boost along the y direction, boost along the z direction, and consequently boost along any direction whatsoever. Okay? So consequently, you have t prime depends on all of x, y, z, t. You have x prime depending on all of x, y, z, t, and you have blah, blah, and so on and so forth. Okay? It's a Lorentz transformation. And you're right, this factor is usually just replaced by gamma. I think this is gamma, right? This is gamma. Okay, this is gamma. I'm going to show you how this arises from our setup a little bit later on. Now, let me just mention one more thing before we quit today. We have shown you that this restriction to SU2, this homomorphism to SU2, does not change the time axis. In other words, t prime is equal to t. All right? T prime is equal to t. I'm also going to show you that x prime will not depend on t. In other words, x prime only depends on x, y, z, and y prime only depends on x, y, z, and z prime only depends on x, y, z, and so therefore it cleanly separates the pure rotations on spatial rotations on the one hand and the things and the kinds of transformations which change the time axis. Okay? So this is relatively easy to do, in fact. Can I take a few more minutes? The class is supposed to end now, right? Maybe we should stop now, because there's another class coming. So that's the idea. That's the main idea. I'm supposed to show you that the restriction of phi to SU2 serves as a pure spatial rotation because it doesn't change the time and it keeps space vectors to space vectors. Okay?